Hello everyone, welcome back. Okay, so this time what we have is a uniform slender rod, and it has a mass of 15 kilograms, and its mass center is at point G. Point G. Now, if you look at this, you're like, wait, where's the mass center? I didn't put it on here, so you have to figure out where that would be for this. For this rod. Now, I wouldn't really honestly call this a rod, I'd call it like a plank, but it is what it is. Okay. So what we have to do here is we're going to find the reactions at pin O and the angular acceleration of the rod just after the cord is cut. So, like always, I'm going to let you go forth and try this on your own, and then we'll come back and you'll see how you did. So how are you going to do it? Well, first off, I'll be nice. The mass center is just simply going to be at the middle of this long beam. So I'm pretty sure you would guess that. And that means it's going to be 0.15 meters away from point O. Now, this point is going to move in a circle around O, and so it's going to have an acceleration that's a normal component and a tangential component. And so just go through and apply that problem-solving procedure to figure out the answer. So 3, 2, 1, you tried it, you came back, I'm sure you rocked it, and let's look at it together. So first off, our free body diagram. We know the weight of this beam is going to be acting through the centroid, and we're going to have a tangential component and a normal component right here. Our kinetic diagram over here says, well, there is going to be a moment around, or an angular acceleration around the centroid, and we're also going to have an acceleration in the tangential and normal directions, which are caused by these forces. So we plug into our equations of motion, and first thing we notice is that there are no forces in the normal direction, which means that my angular velocity in that direction is 0, obviously, and so my normal component is 0, just to start, because it's just been cut, it's not moving. Now that's not the same for my angular acceleration. I can have 0 velocity, but I can still have a positive or negative angular acceleration. So the force in the tangential direction, well, I've got my reaction force in the tangential direction. We have my weight right here. And if I plug in everything I know, which is going to be that the weight is 15 times 9.81, and I kind of plug everything into this, and this was right here is 15, that's the mass, times the distance to the centroid. Then I have one more equation, but that's 2 unknowns, and I only have 1 equation so far. So I go through and I do one more equation. So I know as they sum the moments around that point O, that's important, it's going to be equal to my mass moment of inertia, which is going to be this, times the angular acceleration. So that's going to be proportional. So I plug all of that in, and what I get is that I'm getting a moment. This is caused by the weight. So here's the mass, here's the gravity, and here's my distance. So this is the force, that's the distance. That's going to be equal to my mass moment of inertia times the angular acceleration. So if I plug in everything, using my equations from the back of the book for what the mass moment of inertia for a slender rod is, then I can solve and find out that the angular acceleration is 16.4 radians per second squared, and the tangential reaction force is 110 newtons. 110 newtons. Okay, so that's it for this time. Thank you very much for listening, and I'll see you all later. Have a wonderful day. Bye-bye.